Dear colleagues, welcome you to the next lecture on compilers. And our today topic is syntax directly translation. Syntax directed translation has multiple tools to apply. One is translation scheme, another is syntax directed definition, and finally we are going to go through an implementation of a semantic analyzer, so type checking, by the combination of these tools for syntax directed translation. The examples are from the textbook Compilers, Principal Techniques and Tools. So, the language is typically defined from multiple point of view. The syntax defines how it looks like, and semantics is about the meaning of the text in the input language. In the previous lecture, we went through the definition of the structure of the language by context-free grammars, and we have implemented different syntax analyzers to check whether the input text meets the requirements specified by the grammar. And in the current phase, we are going to go further and check the semantics, so the meaning of the language, and result some intermediate code as well. For example, a kind of translation can be the conversion of an arithmetic expression in infix form to an arithmetic expression in postfix form. The postfix form has the advantage of easy calculation. For example, if we have multiple operands coming one after the other, we place them into a stack, and when an operator comes, we are going to evaluate the operator with the required amount of the operands for the stack. So for example, the operation minus, so the subtraction has two operands, so pick up two numbers from the stack and subtract one from the other and place the result back to the stack. When an operator, so a number comes, we just simply place it to the top of the stack. When we have an operator again, then we pick up the required amount of operators, so in this case two numbers again, apply the addition and place the result back. So in this way we can calculate the value of an arithmetic expression easily. The only requirement is to move the operators from the place where it is in between the operands to the other place where it is after the operands. And as you will see later on, the postfix form exactly defined the order of execution of the operands, so we do not need brackets. And this is the way how some early microprocessor computes. So at that time, not necessarily all the operations were executed on numbers in registers, but instead the processor mainly used the stack and executed operations on the numbers in the stack. Okay, so what is a syntax directed translation? As you could remember, the steps of a compiler, we have first the lexical analysis, then syntax analysis, then semantic analysis, and then the intermediate code generation. In the case of the syntax directed translation, the second, third, and fourth steps, so namely the syntax analysis, the semantic analysis, and the intermediate code generation, are done in a single step. So we are going to set up a code which can perform each of these three steps of the compiler. So after having a set of tokens, we are going to result the intermediate code immediately. Okay, how to formulate the conversion of the infix form to postfix form. First, if we have an expression where we have an operator with two operands and the operator is in between the operands, we are going to transform it in a way that first we have to transform each expression on both sides of the operator and then place them one after the other and finally place the operator in the sequence. For example, if we have here 9 minus 5 in brackets plus 2, which is interpreted as first we execute the subtraction and then the addition. It is written in the postfix form like 9, 5 minus, so this is the point where the subtraction is executed and the result is placed instead of the 9, 5 minus, and finally we have 2 and the addition is executed next. Okay, if we have 9 minus 5 plus 2 in brackets, which means that we are going to execute the addition first and then subtract the result from 9. It is in postfix form as written here, 9, 5, 2 plus. So first we execute the addition on the last two operands, which is 5 plus 2, and then we subtract the 7 from the 9. And as you can see, in this case, not just easy to implement the evaluation of the arithmetic expression, but the brackets become unnecessary as well. Okay, what kind of tools we can apply for this purpose? First, we are going to introduce translation schemes. Translation schemes are practically context-free grammars in which program fragments are included and they are to be executed when the parse-tree is constructed in a well-defined order. The semantic actions, which are these code segments in the grammar rules, are denoted in the grammar in a way that they are put inside braces or curly brackets. So in braces we can write code segments, but these semantic actions, so these blocks covered by braces, not necessarily are on the rightmost of the grammar rule, but it can be included at any place in the right hand side of the grammar rule. So for example, here the semantic action is before the token generated by the grammar rule. In the first two cases, the semantic action is just after the non-terminals and terminals in the grammar rule, and also we can have grammar rules does not containing any semantic action at all. The semantic actions are represented in the parse-tree as well. They are connected to the node representing the left-hand side of the grammar rule by a dashed line. Dashed line are necessary to distinguish between take difference between the derivation and the semantic action. So if we have a parse tree like this, which can define the arithmetic expression 9 minus 5 plus 2. So if we read the terminals from left to the right, 9 minus 5 plus 2, going through the nodes according to the depth first order left to the right, then we get the original sequence of symbols. And then if we execute the semantic actions in the same order, so first we go down here, execute this print which prints 9, and then go through the other childs, and then up to the parents, and go down to the childs again from left to the right. Then we going to print 5 next, and minus next, and 2 next, and finally the plus. So we get 9, 5, minus 2 plus. So if the semantic actions are included in the parse tree, it can define the order of the execution of the semantic actions, and we can verify if the semantic actions are placed in the right position in the grammar rule. And if not, we can modify the grammar rules. Actually, the translation schemes, which includes grammar rules with the semantic actions. And finally, we always get a parse tree when the original nodes represent the tokens. I mean, the leaves of the tree represent the tokens, and from reading from left to the right. And the semantic actions executed from left to the right, we get the output. In this case, it is considered to be the intermediate code. Okay, what is the depth first order? If we have a node, first we go through all the childs. If the child is a semantic action, we are going to execute it, otherwise visit the node. And we continue this loop until we have another child. If not, we are finished, and as you could see, this algorithm is recursive. So if we visit a child and visit its child and visit each child, then we go through and execute the semantic actions in the nodes considered to be the grandchildren and children, and finally at the parent in the appropriate order. Okay, and here we have an example where Roman numbers are converted to Arabic numbers by a translation scheme. So Roman numbers cannot be higher than 4,000, since at the level of thousands we can have more than 3 different digits. M represents 1000, 2m's 2000, and 3m's 3000. And if we have thousands, we start here. We have to distinguish whether the number contains thousands, hundreds, tens, or just a single digit, because in the Arabic numbers we have to place zeros for the position where no number is available in the Roman number. For example, if there are no tens and hundreds in the Roman number, we have to place zeros. So for example, M itself means 1000, However, in an Arabic number, we have to write 1, 0, 0, and 0. So that's why it is important to know whether we have other positions in the Roman number or not. And then the hundreds can be represented in the Roman numbers by C for 100, CC for 200, and CM from 900. And for the tens, we can have X for 10, XX for 20, and so on, XC for 90. And finally, if we have a C which is not at the beginning, so for example, if this is the first digit, it cannot be 0 in the Arabic number. If it is not the first digit, because we have, for example, thousands first and then we have hundreds, then at the place of hundreds, if there is no any number in the Roman form, then we are going to print 0. If we start with this, then the first number cannot be 0. That's why we are going to distinguish A1 from so B1 and B0. B1 is the first digit, so it cannot be 0. However, B0 can be a second digit, that's why it can be 0 as well. Okay, and this is the way how Arabic number can be generated from a Roman number. In the opposite direction, in order to identify the value of a digit, we have to know the length of the number. So if it includes 4 digits, then the first place means thousands, the second hundreds, and then tens and ones. So if we have 3 digits, then the first number represents the hundreds. If we have 2 digits, the first digit represents the tens, and if we have 1 digit, then it represents 1. So we are going into the opposite direction, and at the place of thousands we can have M, MM, and MMM for 1000, 2000, and 3000. At the place of hundreds we can C for 100, CC for 200, and so on, CM for 900. And at the place of tens, if we have 1, it means 10. If we have 2, it means 20. And if there is 9, it means 90, which is described as XC in the Roman number. And finally, the last digit always means ones. So for example, 1 means 1, 2 means 2, which is written by as II, and 9 is written as IX in the Roman number. And also if there is a 0 at a certain position, then in the Roman number we do not have to write anything. Okay, so you can imagine how this kind of conversion can be done. And let's see another tool for the syntax-directed translation, which is syntax-directed definition. In the syntax-directed definition, we can assign attributes for each symbol in the grammar, regardless it is terminal or non-terminal. And also for each grammar rule, we can define multiple semantic rules. Multiple can be 0, 1, or more. So any number of semantic rules for the calculation of the values of these attributes. And we are talking about synthesized attributes when the attribute of the non-terminal on the left-hand side of the grammar rule is calculated from the attributes of the symbols on the right-hand side of the grammar rule, which means that in the parse tree, the value of the attribute of node is calculated from the value of the attributes of its children. Okay, let's see an example. So for example, for the infix-postfix conversion, if we are not going to print out the postfix form, but instead store in a string, and then we can have these three attributes, and these attributes always contains a string, and we can extend the string by a concatenation operation. So for example, if we have digits, and then we can have a grammar rule like an expression plus a term, then we place the string representing the expression in postfix form and concatenate the string representing the term in the postfix form, and finally we place the plus. And similarly for the minus, if we have an expression converted to a postfix form already, we concatenate the term in the postfix form, and finally we place the minus sign. But we cannot generate strings only, so we cannot do string manipulations only, but we can calculate values as well, numeric values as well. Here we have the string conversion, so we have the parse tree with the symbols, actually the tokens, for representing the 9 minus 5 plus 2 sequence of numbers and operators. And according to the semantic rules, the t attribute of term becomes 9, becomes a string containing a 9 character if the child node was a 9, and similarly the expression to term rule indicates that the attribute of the expression has to be equal to the attribute of the term. And if we have a grammar rule like expression to expression minus term, then we concatenate the string at the expression, then the string in the term, and finally we place a minus sign. And if we have another grammar rule applied here, which is expression to expression plus term, and we have this value string and the expression, we just copy it here, and we copy the number 2 here, and finally place the plus sign, and we got the arithmetic expression in postfix form as a result. And we have to know that if we have synthesized attributes, that always the parent node's attributes are calculated from the values of the attributes of the child nodes, then we compute the attributes from bottom to the top, and finally we got the overall result in the attribute of the root of at the root of the tree. Okay, and in this case we have to apply this depth first order as well. So we have to go through each child node first, and then visit the parent node, and at each node we have to execute the calculation defined by the semantic actions. Not the semantic actions, the semantic rules. Okay. And finally, let's see how the value of a number containing multiple digits can be calculated. Here, a number can be a single digit. In this case, its value is equal to the value of the digit. We distinguish again whether the digit can be 0 or not. Term 0 can be 0, and the value as well. If term 1 can only be any digit from 1 to 9, and we practically place the digits one after the other from left to the right, and finally we write from right to the left, sorry, and finally we place the last digit on the left, which cannot be 0 because an Arabic number cannot start with a 0. Okay, and when we place a digit next to an already available number, and we place the new digit on the right hand side, then the number on the left hand side have to be multiplied by 10 to have its correct value with an additional digit, and then add the value of the digit. As an example, you can see here, if we have a single digit, the value of the term is equal to the value of the digit. So if we have a term 1, 2, 3, then the attribute of the term equals to 3. And then if we have a grammar rule expression to term 1, then the value of the t becomes equal to the value of the term, so it will be 3 again. Similarly here, we have the next digit here, which can be 0 as well, but actually it is not a 0, but in this case it is a 6. So we have expression to expression term, and term 0, and term 0 to term 1, and term 1 to 6. So the value of 6 is placed in the attribute of term 1, and then bottom up in the attribute of term 0, and then we have the semantic rule to calculate the expression's attribute as the value of the attribute of the expression on the left hand side multiplied by 10 plus the value of the term 0 on the right hand side. So in this case it's 3 times 10 plus 6, which is 36. And if we apply this rule again, and here we have a 0 at the right hand side, then the value is 36 multiplied by 10 plus 0, which is 360, which is the value of the three digits following each other as 3, 6, and 0. So in this way, and similarly, the value of an arithmetic expression can be calculated as well. During the practical lessons, we are going to go through complex arithmetic expressions, including addition, subtraction, multiplication, division, and also brackets. And we are going to define syntax directed definition for the calculation of the exact value of such an arithmetic expression, which is a building block from, for example, coding a spreadsheet where calculations can be implemented. Okay, if we have these tools, then semantic analysis can be implemented as well by the help of syntax-directed translation. And as we have mentioned in the introductory lecture, the primary aim of the syntax analysis in the case of languages which are programming languages is typically the type checking. Let's see an example where the language is similar to like Pascal or Algol, where we have variable declarations like identifier, colon, type, and each declaration has to be former than the application of the variable. So first we have to declare a variable before using it, and in this case we have declarations and then expressions. Declarations can include multiple declarations, and each declaration looks like variable, colon, and type. In this example, type can be character, integer, array num of t, where t is a type again, or an upper row T. In this case, the array is an array where the number specifies the number of elements and T specifies the type of the element, so each element has the same type and there is a number of them, and the upper row T is a pointer to a value which has the type of T. And if we have constant literals, there could be a series of characters, numbers. We can have identifiers as expressions, and we can write arithmetic expressions like an expression modulo another expression. We can write E and E in angular brackets, box brackets, and then E upper row. Okay. So first, when we execute the variable declarations, we have to know that in these steps, the symbol table is utilized as well. When we have a new declaration, a new entry displays in the symbol table, and not just the ID, but a certain entry of the ID that you can imagine that we place the same variable at multiple locations. And so, for example, if in different functions we can have the same identifier in different functions, we can have a counter called I or J, and we have to be able to distinguish them. And that's why not just the ID, but a certain entry is registered in the symbol table and also its type. And if the type is defined to be character, integer, or a pointer on an array, the appropriate parameters are registered in the symbol table. The pointer, for the pointer, we have to register the type, what it points to, and for the array, we have to define, register the types of the elements of the array as well as the number of them. And if we have a constant containing a series of characters, it is considered to be a character type. If we have a number, it is considered to be an integer. And for an ID, we utilize the symbol table again, since, as I mentioned, first we have to declare each variable and place the type information in the symbol table. So at this point, we can call the symbol table by function lookup, find the entry of the identifier, the actual entry of the identifier, which can result the type. So practically it means that we are searching in the symbol table for the type of a certain identifier. And if we have an arithmetic expression like modulo, then we consider that, for example, in this case, integers are at both sides of the modulo. If it is true, the result will be an integer as well. If it is not true, we get a type error. Type error is a special type value which expresses that the expression includes a type error somewhere. So in this case, if we have a modulo operation, but one of the operands is not an integer but something else like a character, then we cannot execute. So the resulting type will be a type error. And similarly, if we have these box brackets, then we assume that the expression on the left-hand side is an array, and the expression between the brackets is a number, otherwise we cannot look for a certain element of an array. So if one of these assumptions are not true, either the A1 is not an array or T is not a number, then there is a type error again. And similarly, E upper row is the value pointed by a pointers, and in this case we assume that A1 was declared as a pointer, and then the type of A upper row is the type for which value the pointer points to. If A1 is not a pointer, then we get a type error here. And in case of an assignment, we can have just two types of values. Either it is a valid statement or a type error. It is important to note that when we can write a long sequence assignment operations, like in today's languages like C, Java, C Sharp, then the resultant type has the same type as the the expression on the right hand side, but in this current example, this language does not support writing statements in assignments in a long chain. We have to write them down one after the other, and in this case, its type can only be either void if it is correct, so we have the same type at both sides of the assignment, or type error if the two types differ. And we can have a condition expression, and in this case we assume that the expression after the if is a logical value, so its type is Boolean, and then propagate the type of S1 to S. And it is worth to mention here that each of these calculations represents synthesized attributes. So each type attribute is calculated from the right hand side of the view, and then the type attribute of the left hand side is computed accordingly, which means that the type values are propagated in the parse tree from bottom to the top, and finally we get a type error in the type attribute of the root if there were type error anywhere in the program code. Similarly, for the while statement, we assume that the expression next to the while is a logical value, so its type is Boolean, otherwise, and in this case, the type value of S1 is propagated to S. So if S1 is void, S will be void as well. If S1 contains type error, then S will contain type error as well. Okay, if the type of E is not Boolean, we cannot evaluate this condition, and then we result a type error. And if we have a sequence of statements, then each of the statements in the sequence have to be void, otherwise we have a type error somewhere. And if we have a function, then a function has a type of S to T if its argument has the type of S and its return value has the type of T. In this case, the argument has to have the type of S, otherwise we have a type error. But if it is S, then according to the definition of the function with type of S to T, we got back the return value with the type of t, and as a result, the function's type will be equal to the type of the return value, and it is the overall type of this expression. Going back to the previous slide, I have to mention that according to Böhm-Jacopini, if we have sequence, selection, and iteration, we can formulate any kind of algorithm. And as you could see, we went through all these structures of the program code. So first we had the conditional expression, which is the selection, then we had the loop, which is the iteration, and finally we had the sequence, which is a sequence. So we had all the three control structures which are sufficient to represent the algorithm. Okay, as an example for the type of function, for example, if we have the truncate function, which truncates the integer value of a real number, then it has the type of real to integer, which means that it is assumed that the argument will be a real number, and if it is real, then the resultant number is an integer, so the truncate function results an integer. If we check its type, it will be integer. Otherwise, if we, for example, place a character and here and send it to the function, then it cannot calculate its value and results a type error. Okay, so as a summary, we went through syntax directed translation today, which includes 3 steps, starting from the syntax analysis through the semantic analysis, and ends at the intermediate code. And we have seen 2 different tools for this purpose. In the case of translation scheme, the intermediate code was typically just printed. In the case of syntax-directed definition, the intermediate code was somehow computed in values of attributes, but as a result, for example, we could compute values of arithmetic expressions during the translation. And finally, we have seen how a semantic analyzer can be realized by the help of translation schemes and attributes included to compute the type values of each expression. In this case, this type value could be type error as well, and since we had so-called synthesized attributes, which means that for each node on the left-hand side in a Grabber rule, the attribute values are computing for the values of the symbols on the right-hand side. So in the parse tree, we compute the attributes from bottom to the top. If there were a type error in the code, finally we get a type error in the type attribute of the initial, so the start symbol of the grammar at the top of the parse tree. So it results an handy tool to check whether a program code segment includes a type error or not. Thank you for your attention.